I kind of have two talks, but I didn't finish the first one. So I'm just going to mention two key points from the end of the first one before I go on to this talk, which incorporates learning. And the first is, because it really points towards what we're doing and what we've been doing recently to address high dimensions. One is just making the code a lot more efficient. So we had a wonderful industrial visitor, Ken Tanabe from Toshiba in Japan, who spent his year at Berkeley jointly with Mo Chen and another student developing this, what we call BECLs, the Berkeley Efficient API in C++ for level set methods. I mean, the key idea is that a lot of the core level set functionality has been coded now in C++. And we also incorporated the functionality to allow for a GPU implementation of the code, so to parallelize and run it on a GPU. And so I'll skip over the sequential path planning and talk about that a little bit later. But as an example of something I'm going to talk about a little bit later, we get basically 111 times faster if you use BECL's C++ implementation on a GPU. So I wanted to just give that as a note to say we do have, again, the code for the C++ implementation and some examples in our GitHub repository. And then the last point in this first part is a tool that I want to spend a few minutes on now before I switch over to learning, which is something that I've been really interested in over the past few years. It's really the PhD work of Mo Chen, who's the former student who's now at Simon Fraser University, and Sylvia Herbert, who's the one who's graduating now. But this idea of exploring taking an ordinary differential equation and for a reachability problem, projecting it down onto lower dimensional, or projecting the dynamics onto lower dimensional sets of the state space, doing the reachable computation in those lower dimensional spaces, and then back projecting to get either an over approximation of the set or an under approximation, depending on whether you're looking to stay outside of a set or stay inside of a set, or to be able to recompute that set exactly. And I thought what I'd do is explain it using an example. This is something that is best, I think, illustrated using an example. So I'll go back to a low-dimensional example where you wouldn't really want to use this decomposition anyway. It's just for illustrative purposes because we can draw it and illustrate it. And then I'll show you some examples in the second part in this talk, the second talk, which uses this decomposition method to do like 12-dimensional computations, for example, which we weren't able to do before. So this is kind of like similar to the models that we've been using for the aircraft lateral avoidance, a Dubin's car model. And we define the notion of self-contained subsystems. So the idea is that a subsystem is self-contained if all the variables needed for computing the state, the trajectory, the solution, are contained in that subsystem. So you're right, your vector fields contain the variables needed to solve that set of differential equations. So for example, in this Dubin's car, we've got two self-contained subsystems. You're allowed to repeat variables. So we repeated theta, in this case the heading variable is repeated in the two subsystems. And then the idea is to, so you're allowed to couple both state and control. This may be useful. We've worked it out for a number of examples, but it's useful for many systems that have states that are not directly coupled to each other, so that you can sort of trivially decompose. But even when you have this coupling, this could work, and that was the kind of new innovation here. Okay, so suppose that you, in this, go back to the Dubin's car example, suppose you consider these two subsystems. So one is in x and theta, and one is in y and theta. And suppose you could define the target, like the initial data. So in this case, we've got an obstacle that we'd like to avoid, and I can define it in terms of its projections. Namely, it's the back projection of these two sets in either the x theta space or the y theta space. So the pink set is in the x theta space and the green set is in the y theta space. So you assume that your obstacle is representable as the back propagation of those obstacle representations in the lower dimensional space. And then you take intersections of those back projections. So that gives you the overall initial obstacle that you defined. But then you compute the subsystem reachable sets. So you don't do the computation in 3 dimensions. You do 2 computations in 2 dimensions. Right? So here you get 2 computations. This is, this is a problem where the 3-dimensional system is trying to avoid that, the cylinder, the kind of rectangular cylinder. And then you maintain the back propagation of those reachable set computations. So instead of doing 1 3-dimensional, you've done 2 2-dimensional, which is big computational savings because you could do them in parallel. And then that set is, it turns out in this case, it's the exact representation of the set you would get if you did the 1 3-dimensional computation. Okay, so the overlay shows you can, in this case you get, not always, but in this case you get an exact representation. In fact, you probably get a better representation because you're computing this numerically, and it's better to do, a 2-dimensional computation. You get more, fine grained detail than you do in a three-dimensional computation anyway. So you gain, in this example, but the reason to do this is to go to higher dimensions. So something, we could do 6 dimensions if we did very coarse grid, but for an acrobatic quadrotor, we were doing quadrotor flips, you don't really want to use a very coarse grid because you'd like a pretty fine-grained control. And so this one, we decomposed into 2 4-dimensional subsystems. So you can see the shared variables there. So that went down to, 2 times, basically n to the 4 instead of n to the 6th. Then the computations we can basically, do in, 4 dimensions we can kind of do in real time. It depends what you mean by real time. So, we're not dealing in high dimensional problems here, but we're able now to do, I'll show it in the next slide deck, like 12-dimensional computations using this kind of decomposition. And that to us was, for small groups of vehicles, that's something that's pretty realistic, that, it's a very useful methodology to have. You do sometimes. So under certain conditions, you get the exact reachable set. But in general, we're okay if we have an over-approximation if you're avoiding, or an under-approximation if you're staying inside. So we've worked out, they're not necessary, but sufficient conditions to be able to recover either the exact set or an approximate set. And I don't think I'm going to spend much time on this. This is kind of looking at this problem in more general. We published this just last year. And if anyone's interested, I can provide I'll give you the reference to the paper, which kind of develops this in more generality. But each subsystem has its unique variables and its shared variables with the other subsystems. So that's how we defined it. And then, so that's the coupling. And then, we can classify problems in terms of 2 axes. What the control problem is trying to do. Are you trying to avoid a target or reach a target? And then the reconstruction. Can you represent your initial data as the intersection of back-propagated subspaces or the union of back-propagated subspaces? And if you couple the controls, you can solve 2 of those problems. Like the problem that I just showed you, there's 2 we don't know how to solve yet. But if the controls are coupled, which they are in this case, we can solve, we can avoid intersections or we can reach unions. And the details are kind of interesting, but they're, maybe not so interesting in a talk like this. If the controls are independent, we can do all 4 of those problems. So that's been something, it's still work in progress, but we've done enough examples now to tell us that this is something interesting that we're going to pursue working on, and we've used it in a number of contexts. So, this is a 10D system. It's a near hover quadrotor, so it's not deviating much from, it's almost linear, but you can see it's got some nonlinearities in there, gentle nonlinearities. But it's a quadrotor that's kind of close to the hover situation. And we've decomposed that into 2 4D and 1 2D, and then using a technique which I'm not going to talk about that Ian Mitchell has worked on, where you can look at, if you just have a pure integrator, you can basically take that out of the computation. We've got it down to the max dimension is now 3. So we can do that, quite quickly. The challenge now is, okay, we have to represent the set in terms of its projections. So we sort of understand what 3D projections look like. But for higher dimensions, that's more challenging. So I wanted to present that because I'm going to use it in this next talk. But let me just end that first piece, and I've got some acknowledgements that I just want to thank, because it's important to thank all the students who've worked on this. I've mentioned some of these by picture, but these are some former students and postdocs and collaborators who are now at different places or still at Berkeley working on this, and some of the funding agencies that have helped fund this. So let me just switch over now to the second piece, which is really kind of the more recent work that we've been doing on trying to understand how we might incorporate machine learning safely. So within this context of reachability, how might that affect the way we do machine learning for these control systems? Are there any questions? I know I went over this last bit quite quickly, but are there any questions about this?
Just kind of a slightly vague question, but when you show those control systems, the 10D, I'm curious just to have a sense of how many different systems you're talking about. Because if there's only a dozen important ones in this sort of domain, it makes sense to decompose it in kind of an intelligent way like that.
Yeah, so that's a good point, Adam. We were talking a little bit about this. I mean, from an engineering standpoint, and this is what we do in real life, right? We make roads. We make everyone line up so that you're only ever avoiding conflict with the car in front of you. We install protocols, and that's going to be done in an air traffic control system, or if we're designing an unmanned a UAV air traffic control system, which is a project we have with NASA. How do you maintain some of these structures to route UAVs over highways in the sky, for example? There's protocols that are going to be followed. I think that I think if something's sort of 20-dimensional and under, there's ways to handle it. And then beyond that, it's going to be some sort of engineering problem of partitioning, I'll show you something where we're doing a lot using pre-computation. So it doesn't matter if it takes forever if you do it offline, and then get some low-dimensional or lower-dimensional representation of that, which then you can use online. So that's something that we've been doing a lot of as well. But we're all for good practical solutions.
I guess it's sort of engineering versus math. When we present the stuff in math, we're trying to solve every control problem. But just from what you've shown here, it sounds like there's actually several important specific ones. You're not trying to do everything all. You're not trying to write a general purpose solver for all 20-dimensional things. You've got specific systems.
Yeah, I think we're a little bit in between. I mean, I would say with Ian's toolbox, we were trying to he did it, right? So he was trying to make it as general purpose as possible. But, that's within the context of ordinary differential equations, and with the knowledge that, if you go beyond 5 dimensions, you don't typically have enough storage space on a typical computer to run it. So yeah, there's practical limitations there. But I think you're right. We've been motivated a lot by problems that, where we need these solutions, but we can make some assumptions that allow us to put it into lower dimensions in many cases.
So,
yeah.
Before you consider like the case where the subsystem are coupled or independent, but it seems like that one is independent and the other is coupled in the previous one. I mean, my question is, Yes, there is also the case of fully coupled.
Fully coupled.
Yes.
They can be coupled as long as the subsystem has all the variables it needs to compute a solution. So you're allowed to share variables across subsystems, but in order to be able to get those results, they have to be you have to have some restrictions on how those variables are shared. So coupled is allowed. That was the cool thing that we found, that allowed us to do these higher, but not real. It's not like a mean field game type problem, or the typical problems you're looking at in mean field games, which we were talking about yesterday and today. Okay, let's go to the second talk now. It's towards real-time reachability part 2. Okay, and I won't go over the motivation again. I just put one slide of motivation just in case to remind us what we're looking at here. But even in that air traffic control problem, the sectors of airspace, each air traffic controller typically has at most 12 aircraft that air traffic controller is dealing with at any given time. And that's extreme. So, it's typically maybe 4 or 5, maximum 12. So it's, reasonable. And because of the routes, they're paired. So you may have 3 or 4 aircraft coming together at once, but you don't typically have 12. But who knows? I mean, we're at a point now where new designs are being taken into account. So we'd like to consider as high dimensional as we can. Okay, so I'm going to continue this for the second part of the talk, the discussion of reachability. We've spent some time on that in the last talk, so I just have a few slides just pointing out some of the pertinent details for this part of the talk, and then continue with focusing on this talk mostly in learning and incorporating learning into reachability. Okay, so we talked about this last in the first hour, so the concept of the backwards reachable set as a game. And we talked about the level set interpretation. And the new point I'd like to add now is this idea of invariance. So if once you've computed that set, so if you've actually solved over the infinite time horizon, and you've got a function j of x, so it's no longer time dependent. And that means it's controlled invariant because regardless of the time horizon, you're guaranteed that if you're outside of that set, you're going to stay outside of that set for all time if you apply the appropriate control. So if control invariance holds, meaning maybe that set closes after there's some finite time, that set just sort of closes in on itself and stops growing, then what you have is that any super zero level set is also invariant and may also be used for safety. Okay, so over approximations of that set work, but in particular, super zero level sets of that set can also be used to certify safety. And then the other point that I wanted to raise again is if you have the control invariant situation, that the more you know about the disturbance, so the closer together the bounds are on that disturbance, the more the less conservative that set becomes. So the more you know about your opponent or about disturbances in the system, the larger the safe operating space is. And that will come in. We'll use that in a few minutes. Okay, so this is. Again, this is just showing now here we have 4 quadrotors, and the students are piloting each quadrotor around, and they're instructed to try to cause the quadrotors to collide. But so what I've plotted here are each quadrotor, and this is just a snapshot at a particular point in time, with the reachable set with respect to the other 3 quadrotors plotted around it. So each quadrotor's got 3 sets around it based on its knowledge of the current state of the other vehicles. And these sets are moving as the quadrotors are flying around. So in this algorithm, or in this implementation, when one quadrotor gets to, say, the boundary, or its the boundary of its reachable set with respect to a second quadrotor, then the automation on board takes over and uses the optimal control to guide them away from each other. So it's like that 2 aircraft problem that I talked about before, but now in this case, we're able to actually solve this problem for 4 aircraft because of the dynamics of the vehicle. Because quadrotors can stop, and well, they can't stop, they can hover, then you can guarantee that the union of these 3 sets represents the exact unsafe set for this particular problem for each aircraft. And that's a nice proof. We're not going to go through that here, but there are certain, it depends on the dynamics of the problem you're looking at, but in general, the vehicles are, the way the dynamics are configured, there's no situation where having like more than one opponent that ability of those other vehicles to collude with each other will actually increase the size of its unsafe set more than just the union of those 3 sets already. And that's an interesting special case. So that was one case we worked out. But in general, this high dimensional problem, as we've talked about, as you add more and more vehicles, if you can't make this assumption, it's hard. Okay, so this kind of brings together some of the things we've talked about already for dealing with this curse of dimensionality. The first thing is what we were just saying. You can impose practical constraints, like we have roads, highways, protocols to make sure that interactions remain between smaller numbers of vehicles. And there's quite a big community of people working on this. So a lot of people have worked on not just Hamilton-Jacobi methods, but computing reachable sets for different kinds of systems in general. So in this approximations, there's a lot of work by people who will assume the dynamics are linear, or assume that the sets are polyhedral or ellipsoidal, and then over-approximate the dynamics with linear, so that you can essentially solve some of these problems analytically. And so that's been done. There's a lot of work going on in barrier certificates, so using control barrier functions. And we have a nice collaboration now with a researcher at Berkeley in mechanical engineering called Kaushal Srinath, who works on walking robots. And he's been working on a lot of control barrier functions. But the challenge there is, it's like a Lyapunov function. You actually have to come up with it. So you have to try to figure out ways to come up with this function. And the reason we're working together is we believe that these Hamilton-Jacobi methods are ways to propose control barrier functions to use. And the idea is very similar to, keep out sets using barrier functions is similar to keep out sets using Hamilton-Jacobi methods. But there's some numerical advantage to using barrier certificates. I mean, there's some analytical computation that you can use because they use, they make assumptions like they're polynomial systems or they're sum of squares or something like that. We talked about decoupling. So we talked about decompositions, and then something similar that I didn't spend any time on was decoupling disturbances. So ways to break down the problem into smaller problems and then assume that the variables that you're not considering are disturbances in the system you are considering. So that's some work that we've been doing. You can employ if you know something about the mathematical structure, like the differential equations are monotone, then you can employ some computational savings tools there. This is actually a very interesting topic, and I think that Jérôme's talk yesterday really was an example here, where let's use machine learning in a really intelligent way to solve these equations faster. And there's been a bunch of cool work that's been done quite recently in this area. So I'm going to talk about some of the things that we've done to really push this into higher dimension, but as it pertains to incorporating machine learning. Okay, so the first thing I'm going to present is this idea of using an intelligent pre-computation for using reachability in real time in robotic path planning. So we call this, we actually call this fast track for fast and safe tracking. But we started out thinking of, robotic path planning. And there's these different schools of thought, depending on whether you're kind of coming from the control theory point of view, which is the column on the left-hand side. You want to be accurate, so you're kind of forced to be slow. If you use a full dynamical model of your system and optimal control, you're going to be slow because the models are, pretty high dimensional if you consider all the variables. But it'll be accurate. You'll get a path, and you'll be able to track that path pretty much perfectly using the control law that you've computed. This is counter to what's typically done in robotics, which is fast but less accurate planning. I mean, a lot of what's done in robotic path planning is like, sampling points and then connecting those points and then trying to generate feasible paths. And, it typically works really well, except you're stuck with large errors. So, a path might be the blue dashed line, and then when you track it, because you don't have a bound on how far you are going to be away from that path, or you may have some bound that you just guesstimate, you might violate the constraints. So what we thought we could try to do was bring the two techniques together, the sort of left-hand side and the right-hand side, using Hamilton-Jacobi reachability. And recognize that this is using a high dimensional, maybe it's like a 12-dimensional model of the system. And this is assuming you want to do something a little more interesting than just fly around. Following a lateral path, you've got vertical dynamics that you're interested in. And this might just be using, a 3-dimensional point mass. So what we thought we would try is have two models, the high-dimensional 12-dimensional model and the 3-dimensional model. Those are two different models of the same system, but let's set up a pursuit evasion game between those two models. And let's make the high-dimensional model try to capture the low-dimensional model. So that's a reachability problem. And let's use reachability to compute the worst-case tracking error bound between those. And as long as you don't have obstacles, you're flying in free space, that computation is invariant, meaning that you can, invariant in the sense that you can perform that computation ahead of time, compute a tracking error bound, and then plan using a fast planner with your tracking error bound. You just carry that tracking error bound around with you. So then just do fast planning with a pre-computed tracking error bound. And don't allow the system to go into areas where your tracking error bound is too big.
It's just like a bubble that goes around.
It's a bubble, but it's a bubble in this high-dimensional space. Because if you're looking at, you compute the relative dynamics between, say, a 12D model and a 3D model, it's going to be a 12D set. And then here we project it down into the whatever the planning coordinates are. So, so we did this. This is basically, you can set it up, as I said, like a standard reachability problem. The planning system is trying to get away. It's trying to maximize the cost. The tracking system is trying to get to where the planner is, so it's trying to minimize the cost. And you just capture the maximum cost over time. So this is an example of in this case, we've got a 7D model tracking a 3D model. It's more for visual than anything else because I want to sort of illustrate here what we can do. So the pre-computed tracking error bound. Suppose, for example, that you had 3 possible tracking error bounds. So a large, medium, and small one. You could look at that computation that we just did, and you can say, all right, are there any states for which I'm guaranteed on this computation to stay within this 0.5 meter, the smallest tracking error bound? Does any part of this set remain control invariant under that computation that I just described? And likewise for the 0.75 or 1. If I've got some states here, then I'll have some here and here. But if we look at that computation from this point of view, So here's the reachable set computation projected into these spaces. What we're essentially doing is carving out regions of these levels which are invariant. So in this case, for this example that I used, there's no, you cannot maintain under any circumstances a 0.5 meter tracking error bound between this high dimensional model and this low dimensional model. But there is some subset of the 0.75 meter ball and more of the 1 meter ball. You know, these sets are just, you know, they're computed from this. We're looking at slices of these sets in this two-dimensional space. So, and those are the sets that remain invariant. Those are the sets that we can like carry around with us. So this computation would say, well, if you want to maintain a 0.75 tracking error bound, you can do that. You can, you know, apply this technique, use 0.75 as your tracking error bound. You not only get what that invariant set looks like, you get the control law to keep it invariant. So as your tracker is trying to track your planner, if it starts to get close to this boundary, so it's got to be in this region, if it starts to get close to this boundary, the boundary will tell you what control law you should apply to get back close to the, or within 0.75 meters of the planning state. Okay, so this is that example that I showed you before of a 10-dimensional near hover quadrotor model. This one is actually trivially decomposable because there's no coupled variables. You can see there's, you know, 3 distinct subsystems which are where there's no variables shared. So we did this, we did 2 4D computations and 1 2D computation on this one. And then, so that's our high dimensional model, and it's tracking a 3D point source. So we computed the relative model between those two, which is, in this case, a 10-dimensional model. And then we just applied that pre-computed tracking error bound, which when projected down, so that's a 10D set, but it's now projected down into X, Y, Z space. So now we've got, this is our, you know, the green star represents the planning state. The box represents the projection of where the tracking state could be, but that's a guaranteed box. And now we can just use any planner we want. So we use this rapidly evolving random trees planner, which is essentially kind of like, you know, you find a bunch of points and then you set up straight lines between them. So here it is discovering obstacles as it goes. It's trying to get to that blue circle on the right of the screen. So it allows you, by computation of this Hamilton-Jacobi tracking error bound, it allows you to use these fast planners and just carry around this pre-computed tracking error bound. So you don't have to do the cumbersome slow planning of a 10D set, or even, you know, in this case, a 4D set. I think the cool thing is that now you can actually switch between different planning models. Say, you know, you had a 10D model and then a 3D model. And the 3D model, you found the tracking error bound was really big and, you know, you wanted to go down narrow corridors and stuff. So what would you do? Your natural thought would be, well, increase the dimension of the planning model. Let's maybe put some kinematics in it. Let's make it a 5D model. So now I've got the difference between a 10D model and a 5D model. I expect the tracking error bound to be smaller because I'm using a more detailed, I'm using a planning model which is a bit closer to the actual dynamic model of the system. And so then that slows down your planning, but the idea might be if you're kind of in a wide open space where there are few constraints, you use the low D planning model, so you do planning fast, and then you see that you're coming to an area where, you know, the corridor is a little more narrow. So using reachability, you can figure out when you should switch to that the second planner, which uses the slower model, so that by the time you get to those constraints, your tracking error bound is small enough and you're guaranteed to be within it, because you have to sort of get to that smaller tracking error bound. And so that's exactly the kind of computation that reachability allows you to do. So we did that. We've got these implementations. This is our little quad rotor. We now moved to indoor smaller quad rotors. But this is just going through a wider tracking error bound, and then it's going through a narrow constrained space, so it switches to a smaller bound. And we have a group at Berkeley that's interested in this AR/VR. This is augmented and virtual reality systems. And they're working on intuitive ways to set up waypoints and then do path planning for robots in a kind of a virtual world. But the actual that is being fed to an actual vehicle that's flying around in the the real world. So this is Jesse who set this up. And what he's doing now, you can see what he's doing on his virtual screen as well as in real life. He's setting a bunch of waypoints through an obstacle course for quad rotors to fly. That funky stuff is just the edge of the virtual world. And so that defines a path. That's like our typical robotic path. And then behind him, so he launches it, behind him is that obstacle course. So there's our little quad rotor, and it's basically flying this, it's tracking this path. So it's using fast track to compute the tracking error bound ahead of time to show that that bound is small enough to both for the switches as well as getting through those hoops. All right, so with that background, I'd like to start moving into learning. And we did this in a sort of progressive way. The first was something that's really not using learning very much at all, but it's a Bayesian update on parameters and how we incorporate that. So this is the idea of taking that planner fast track for fast and safe tracking, so the pre-computed tracking error bound using reachability, and applying it to planning around more complicated obstacles, not just static obstacles, but people. That's one of our challenges, is trying to fly robots or drive robots in areas where people are moving around. And so this has been a project with a number of students over the past few years. It also involves Sylvia Herbert, who has worked on fast track and these decomposition methods for Hamilton-Jacobi. And we really just started with some of the methods that have been used in both the more like the mathematical psychology as well as robot motion planning communities for predicting, in this case we're looking at navigation, so we're predicting motion of people that are walking around in spaces that look like university labs. So it's quite specific. But they're moving around, and they're assumed to be goal-oriented people. So the people in the lab have goals, and we're assuming that we can either identify a candidate set of goals, or there's that's given to us, and then we watch what people are doing, and we update their models, their predictive models, based on their motion. So this is a model that is. You probably recognize this. It's this Boltzmann model. It's a model that's been used a lot in this robotic path planning community for predicting human behavior, and in particular in walking motion, or also in the autonomous car companies are using this to predict motion of human-driven cars. And the model basically says that the probability of the human's action, so this is the control action of the human, becomes more likely the more efficient it is for a particular goal. So the Q function here is encoding our value, and the value is a function of a parameter theta, where theta measures the goals. Okay, so our theta represents the goal. So here in this little stylized diagram, there's one goal which represents the door, theta. And so actions that the human takes which are efficient for that goal become more likely under this model. And then beta is a scalar. It's a positive number, just a real number. And it's this, in the Boltzmann, the original Boltzmann model, that's the inverse temperature the inverse temperature coefficient. So beta is something that we can actually play with. So, you know, small beta means the person isn't really being rational. Their distribution is going to spread out. High beta, as beta gets higher and higher, it means that distribution becomes more peaked, and the person is actually doing something which is, you know, rational towards the goals as stated. So you could have multiple goals here. We're just showing one. So in this case, you know, the pink region would represent regions of high probability, and the blue would represent regions of low probability. Okay, so here this word that I use, rationality, is actually, rather than being rational, it's more like how well is our model representing the person's actions. So it's like model confidence. And so beta, you know, the value of beta can represent the spread of that distribution, of that Boltzmann distribution over time and space. And it's something that we can update. So if we're, you know, if we're that quadrotor and we're planning a path and we're trying to figure out where the human's going to be in the next few time steps, we can parameterize their action using this probabilistic model or another, but this is the one that we chose. And then we can ask how rational is, or how confident are we in this model? And if the human's doing actions which don't look rational towards that goal, we can just update that parameter beta. So that's really what we did. We're, in a sense, it's a learning problem, but not really, because we're really just doing a Bayesian model confidence update on that parameter beta. So here, you know, say the person turns around because they forgot their keys, they're doing something which is irrational according to this goal, so beta would be updated, causing the distribution to spread out, saying, oh, I don't know what they're doing now, so I'm going to be a little more careful when I'm planning. I'm just making my obstacle a lot bigger. Okay, so that's kind of the thought that we had in treating, our first step in treating humans as obstacles in these Hamilton-Jacobi planning problems. Okay, so here's an experiment. This is Sylvia, who you've seen before, and she's our human being test subject, and she's moving towards the door, which is her goal, and the quadrotor is trying to plan around her. But there's a spill, maybe a coffee spill on the ground, and that's something that the quadrotor doesn't know about. So it's using this updated, this model to update the beta parameter on Sylvia. Let me just play that again so you can see the spread. And what was sort of a peaked spread towards, what was a peaked spread towards the door rapidly became wider as she started moving away from a straight line path. So this is the next few steps in the Boltzmann distribution. The blue path represents what the quadrotor is doing. So that's what actually happens, and then we'll look at that top-down view again. Okay, so the blue path represents quadrotor motion. So as she starts to move, that distribution spreads out quite a lot. You see a lot less pink when she starts to do that. And then she starts to move back towards the door, and it starts to get more pink again. All right, so we can actually apply this now for multiple people. We just we decompose the problem. So here, this is Sylvia, and that's Jaime. They're both trying to get to their goals, which are across on the other sides of the room. And there's two quadrotors now. So we have the first quadrotor and the second quadrotor. So they're all trying to go in a, like diagonally across the room. And if they didn't do anything, they would all collide in the center. And what's interesting is you see, Sylvia and Jaime getting close to each other, they pause, so they're kind of moving around each other. And while they're pausing, the distributions of both naturally spread out because they're not moving towards their goals anymore. So it kind of captures, without doing anything, this multiple person interaction. Likewise, the quadrotors themselves are using fast track. And what we're using here is a sequential path planning algorithm for the two aircraft. So they know where each of the other aircraft are, and we have a priority-based sequential path planning algorithm, which was one of the contributions of Ken Tanabe in using this Beacles toolbox that I talked about earlier. Okay, so let's just let's finalize this just by looking at this one. So we're sort of showing both at the same time, both quadrotors, and you can see Jaime is always a little more uncertain because he's dancing around. He's going a little bit slower. He's not following what the quadrotors think he should be doing. But you know, in this case, the quadrotor actually paused so the Jaime could go past before it planned the rest of its path towards the goal. Okay, so each time they're using this pre-computed reachability-based fast-track planner, and they're calculating now it's the probability of collision by looking at the potential intersections with the Boltzmann distribution. So we truncate that distribution, and we look at basically thresholding when there's going to be an intersection between where the person could be and where the fast-track tracking error bound will be at that time. Okay, so that kind of moves us into the learning part of the talk, and that's really the last half hour of this presentation. But before I go there, are there any questions on, you know, anything we've done so far, the setup, the computation, some of this pre-computation, decomposition, some of these ideas we're trying to use to improve the scalability of this method, or its use in real time? Yeah. How they can react to the... Yeah, so that would change the tracking error bound. So beta would just be, beta is like what the person is doing, but that would change the tracking error bound. And so in some of our experiments, we've done exactly that. We've used, you know, the same models, the tracking model and the planning model. We use the same models, but the tracking model had a much the tracking model had a much slower reaction time than the planning model. So you could see the difference, and you know, that's just going to compute a tracking error bound then. So yeah, it's generic. You could use it for, you know, even for the same model with different speeds that they're flying at. Okay, so learning dynamic behavior safely. This is the last part of the talk. And as I've been doing all along, I'm going to present this through examples. And we've done a couple of steps here. So the first thing we worked on, where we used a very simple learning algorithm. This is by Zico Coulter and Andrew Eng. They published it back in 2009, Policy Gradient Sign Derivative. So it's a very simple online learning algorithm for trying to learn the parameters of a dynamic model. Well, okay, we're using it in the context of learning the parameters of a dynamic model of the system by collecting data about how that system is operating. So I'm going to describe the setup of this. This is a quadrotor, and it's flying in a room, and we're just asking it to fly a step trajectory up and down and up and down. And it's the safe set that it's computing is a flight envelope within the room. So it's trying to stay inside a set where it doesn't want to crash into the ceiling and it doesn't want to crash into the floor. So it has an upper limit and a lower limit in terms of space. And then its vertical velocity, so its model in terms of its height and its vertical velocity. As it's getting close to the upper limit, it has to trim down its vertical velocity so it doesn't go through the upper limit. Likewise, as it's getting close to the floor, it has to lower its vertical velocity so it doesn't hit the floor. So it's really a simple idea. We just do that simple. It's like a double integrator reachable set, but it's like the vertical dynamics of the vehicle. So we pre-computed that reachable set. And then we took the model away from the vehicle. So we assume we had it, and then we kind of somewhat artificially took the model away. And we asked the vehicle to learn its model and its control policy to track this trajectory, this up and down step trajectory, while staying in that reachable set. So it's a kind of an artificial thing because we took that model away, yet we left the reachable set. So it knew when it was going to hit the boundary, or it knew about the boundaries, and it knew what control law to apply on the boundaries, but it didn't know what to do when it was away from the boundaries. It had to learn that so that it would effectively track this step trajectory. All right, so this is...
Policies, but also learn the dynamics.
It learned the policies which were based on the dynamics. So it learned it learned a simple dynamic model of itself. We gave it the dimension of the state, so it was learning the vector field. Okay, so it first drops, but it doesn't hit the ground. It drops because it doesn't have a control law. The blue dashed line represents what it wants to track, so it speeds up a little bit. So it's sort of bouncing around at the bottom of that envelope, and it learns, from that what thruster it has to apply to go up. And so it learns using this really simple algorithm pretty quickly. After about a minute, it does a fairly good job of tracking that trajectory. And here, the red indicates when it's using the safe control law. So you can see, and predominantly when it's coming down, it's trimming away its vertical velocity so it doesn't violate the floor of that envelope. Okay, so so that was more of let's try out and see what happens when you apply in a kind of, I keep saying it's artificial, it is, but it's just showing that you can, in a very simple way, as long as you're operating away from the boundary of this envelope, you could use a learning algorithm to learn about parameters of the system, the dynamics, the control law to track something, etc. Okay, so, but that's not so interesting. Usually we want to do something in real life where we're learning actually about you're learning more about the system so that you can update the envelope, right? You want to blend together in a more interesting way the reachable set computation with the learning procedure itself. And that's what we're working on now. This is a step towards this, which we call online disturbance model validation. And for this, I kind of went back to that animation that we started with today, where we've got an unsafe region, we've computed its level sets, we've computed the value function and we have its level sets, including these super zero level sets. So we'll come back to that point. So and then we start running the system. So we initialize the active unsafe set with the smallest candidate set. And then we repeat. We run the system and we collect data about the system. So at each data point that we're collecting, we're measuring the disturbance. So we're assuming, there's parts of the dynamics, namely the disturbance, that we don't know. And we'd like to get a better model of this disturbance so that hopefully we can reduce the bounds on the disturbance and make that reachable set less conservative than it was before. Maybe do something that allows us to approach what might be like, the optimal set. So this is a departure from everything I've been talking about before, because before we just assumed that we had bounds on everything. We assumed we had bounds. We didn't know what the disturbance was, but we had bounds on it. Now we're admitting that we don't know what that disturbance is, and we're collecting data to try to get better estimates of it. And at some point, we're going to use those new estimates instead of the old estimates. So it could go both ways. I mean, in this case, this is meant to show, we get a point that's, outside, that's in what we thought was safe, which is actually violating our safety. It's violating our disturbance assumptions. Like, whoa, the disturbance here is much bigger than I thought it was. I better expand. So expand the unsafe set. So it expands to a super zero level set of that value function. So it coincides with the point where you first measured that disturbance was violated. Now you've got a level set which corresponds to the disturbance values that you're measuring in real time. And so this is this sort of Bayesian update that we use to do that. Over time, you might expect that as you get more and more data, that if you started out with a conservative approximation of the disturbance, that is, you're going to get a better and better approximation, and you may actually get a smaller unsafe set, so a less conservative solution. Okay, so now that same experiment, but a little bit different. So now we're asking it to follow this step trajectory, but we've put a big fan in the room that provides a disturbance that the system didn't know about when it computed its reachable set. So it's a quadrotor, and you'll see two experiments here that we ran sequentially, and I've superimposed them on top of each other so you can see the difference. You'll see the fan being turned on, and that creates, it's a big fan, kind of a big wind disturbance here that's outside, that provides a bigger disturbance than was used in the computation of the original reachable set, which went down to the floor, or close to the floor. Oops. All right, so it's going a little bit slowly here. Here's Kene Akamatalu, who's a former PhD student who worked on this with Jaime Fizak. And this paper is now in the IEEE Transactions on Automatic Control. So he turned on the fan, and now the vehicle's coming down. And as it gets close to this disturbance, you'll see these two different experiments. So the ghosted out one is the one where we don't update the reachable set according to the algorithm that I showed on the previous slide. Namely, it keeps that reachable set according to the bounds that, the disturbance bounds that it thought, and it bumps into the floor at some point. What happens with the second experiment, which is the non-ghosted out one, is it's basically shrinking back the safe set, just like I showed in that picture, to the point at which the measured disturbance complies with the sub-zero level set of that, or it's a super zero level set. You're looking inside an envelope of that function. So that's the next step beyond trying to blend together learning algorithms with these safety envelopes. And the safety envelopes are kind of like bookkeeping, what you know about the system. I mean, there's all sorts of questions about learning rate and how do you update these, and that's going to be system dependent. But I think this reachability is a way to record and bookkeep what is safe about a system and maintain that even through the learning process. Okay, so the last point here is now this is maybe approaching this from the other point of view, is where do we really want to use machine learning in these control systems problems? It's not really for what I just showed, right? I mean, control theory as a field has done a really wonderful job of treating disturbances. Even if they appear, we got adaptive control, we don't, and a lot of the control field, I feel a little bit to its detriment, has been saying, oh, we don't need to use machine learning, we've been doing adaptive control for years, blah, blah, blah. Okay, where I think we really need to use learning, and we talked a little bit about this morning, is in unstructured environments where you don't know what you're going to see. You don't even know what disturbances might be out there. And as I said, the field of computer vision has really moved over towards machine learning because it's a very effective way of capturing image data and interpreting and perceiving image data. And we really want to design control algorithms which work with such systems. So with a couple of my students, we took a little bit of a departure from reachability for a little while. And we said, okay, let's just think about a control architecture with a neural net in the deep learning mechanism in the loop. And then let's think about safety of this. I mean, what we just talked about learning to fly when we're just learning a disturbance, doesn't really apply here just because the disturbances are, things that suddenly appear in your path. How do you model that as, something that comes in nicely on the right-hand side of your differential equation? This is the experiment that I'll use is just a mobile robot. It's got an RGB camera on board, and it's trying to go to known goals, but everything between its current position, which it knows, and the goal, which it knows, is unknown. It doesn't know what's, the furniture, it doesn't know the layout or anything like that. So we've been working on this. This is the PhD work of Saumil Bansal, who's graduating also this year. This is the first part of what he did, which was to design an architecture which, counter to many of these end-to-end learning schemes for control, which have been coming out of the machine learning community, it says let's leave learning to perception, but let's blend it nicely through an interface to really standard planning and control, the kind of fast track type or control laws that we've been talking about throughout this talk. Because then you're not really learning, you don't learn things you already know, which are the models and the control. You learn what you don't know. So this architecture, the camera takes an image, it feeds it through a convolutional neural net, and it outputs a waypoint. That's a next waypoint to move to going towards the goal. How to train this was that's what took the 2 years that we worked on this for. We used optimal control to train that perception module using a bunch of simulated data. There's the Stanford Indoor Spaces data set that has mapped out 5 of their buildings. So we trained it on 3 and we tested on 2, but then we took that system that was designed entirely on tested simulation data, and we applied it to the real open spaces at Berkeley in indoor buildings, which are still their indoor buildings, but albeit a little bit different than Stanford's buildings. So trained at Stanford and tested at Berkeley. Yeah, but and it's interesting because the chairs are different. Stanford has fancy chairs, and Berkeley doesn't have. So it keeps bumping into chairs. But it's just I'm not going to talk in detail about the methodology that we used for training this and the different architectures we chose, etc. That's the subject of another talk. But I'd like to get to the safety analysis of this. So we did a little bit of comparison with end-to-end learning just to show that it's better. Finally, and where success rate, so where end-to-end fails.
Meaning it's learning everything.
Yeah, I'm sorry, I should have defined that a little bit better. So end-to-end, when I give this to a learning audience, they immediately know what end-to-end means, but it's not obvious, is it? So end-to-end means that your neural net goes all the way from image to control action. So pixels to actuation, whereas we're going from pixels to waypoint. And waypoint is something that we're used to getting. The control community loves getting waypoints because then it can do planning and control and knows how to do that.
And that's because computer scientists don't know anything outside of computer science.
No, I don't think that is. I think it's because they are in these past few years where deep learning has been applied to robotics more and more. There's been this kind of fun cowboy attitude of let's see what we can make the system learn without using any control theory. And it's been a very convincing argument that learning is, like you said, you get very high performance, but its failure cases are also spectacular. So you see a lot of the videos about the high performance and what it can do. But it's also, you don't see this sort of more boring stuff about the sample efficiency of this learning. And I think now, the way the field is going, and we've organized a few of these learning and control conferences now, is that there's much more of a movement towards, really integrating the two together. So using learning, so sort of like this,
Okay. So they're looking more towards this direction.
Yeah, well, some are still doing end-to-end, but I think it's pretty clear that this is not just this, but algorithms which blend learning for unknown with not learning for known are, the things to do.
It was very confusing to us. All the reinforcement learning people we know in Montreal, they just want to go end-to-end.
Yeah, I think part of it is this showing what learning can do. And I think that's a valid thing when something's really getting going, is look what we can do. And that's the phase. I feel like we're coming to an end of that. Maybe it's just because I'm working on this now and I feel like, okay, we published this in the Conference on Robot Learning last year. And by then, in those 2 years, there's been more and more groups that have moved towards an architecture similar to this. Let's just show a few of these. Okay, so this shows a couple of different views. This is the robot. These are the images that the robot gets. This is just for you to see the robot, so you can see the third-person view, and then you see a top-down view where the green represents the goal. So remember, the goal is known, but none of the stuff in between the blue origin and the green goal is known. It's learning that or it's not learning that, it's perceiving that on the fly, and this trained neural net is giving a next waypoint based on, similar scenarios that it's seen in the simulated system at Stanford. We trained it completely on static systems, but then here's Varun, who is one of the researchers on the project, kept changing the obstacle, so moving it to other scenarios. And the obstacle is moving at a slower rate than the vehicle is, so it's able to deal with that. We're now actually asking it to learn motion of people, and we created a simulated database of people moving around, so we could train it on a lot of people data. Couple of lessons learned. I think actually this is the most important or most interesting part of this before we go to safety, is that, and this was important for me as I was getting into this field, the data representation is important. So whether you work in an inertial frame or a body frame made a big difference to the efficiency of the learning procedure. We trained the neural net using optimal control, but optimal control, as we know, can be too optimal. It loved to sort of skirt corners, so that obviously was bad for training because the thing kept crashing into corners. So providing buffers like fast track would. And the waypoint representation is important. Waypoint is our interface between the perception module and the planning and control. So, even for this simple navigation scenario, whether we're just using X, Y versus using X, Y, and heading made a big difference. And we're now trying to implement this on board Kaushal Srinath's walking robot, where the waypoint now is going to be much higher dimensional than just because it's got all these states of this Cassie walking robot system. Just this navigation problem.
But you're saying the one where it also has an orientation worked better?
It worked better in this Turtlebot scenario, but now with the Cassie robot, it's going to need, I don't know, we're working on this right now, but the Cassie robot, the walking robot, is replacing the Turtlebot. It's got a camera on board. So now waypoints should be probably higher dimensional, have some of those body dynamics in it.
Which was better on top, the inertial or the recursive?
The body coordinates were much better. Some of these are empirical, so, but some of them, they make sense when you look at it post-analysis or post-empirical analysis.
Can you go back where you compare with end-to-end?
Yeah.
I just like to understand the metrics you use.
Okay, so the success rate in reaching the goal. The model-based method, which is ours, had an 82% success rate versus a 56% success rate for end-to-end learning. Now, of those that were successful in both, so the remaining 3 plots are comparable. We just chose the successful ones in both. The time taken to reach the goal is shorter for model-based. These are intuitive because we're using a model, right? So the average acceleration and the average jerk is, we measured those because these end-to-end, the reason we're doing this is because one of our colleagues in computer vision said, we've really got to do something better in control because when we use end-to-end, you get these really jerky control profiles. So that was something that was expected when we did this.
Wow, look at that.
Yeah, it's not surprising though, because we use this and, I mean, that...
They didn't put anything in there to decrease
No.
acceleration.
No, we actually did when we were, so this comparison, we even put in filters to try to decrease the, in the end-to-end learning, the acceleration and the jerk, and it still didn't perform as well. Okay, so I'd like to end on just incorporating safety now. And this comes back to maybe chairs at Stanford versus chairs at Berkeley. So here's a case, oops.
I'm waiting for the joke about private, public funding.
Yeah, no, I like both places, so I won't say that. But ideally, you'd like to be able to, so now we want to be able to prove that, the system stays away from obstacles and reaches its goal. But now we're doing this in real time, and we're, perceiving the obstacles in real time. So we have one channel that's using this convolutional neural net for perception, and the big problem is, as you pointed out this morning, what if your perception is giving you the wrong thing. What can you do? I mean, right now, that architecture that I showed is not safeguarding against that. So what we're envisaging now is having two channels. We've got the CNN, which is running the convolutional neural net, which is running based on the RGB image. And then we also have a depth sensor. We actually computed depth using 2 subsequent images of the RGB. And we use that to create a kind of SLAM type environment, indicating where obstacles are and where free space is. And then we updated the safe operation of the vehicle based on that SLAM channel. Okay, so let me explain that a bit more. So suppose the camera gives you information about where the obstacles are. So you've got, your CNN, which is just giving you a waypoint. But now you've got a more traditional SLAM-based architecture, which is also giving you information about free space and obstacles. And so that can be turned into a value function, as we've been talking about all afternoon, for initial data for a value function to be computed using Hamilton-Jacobi. So the gray here represents the obstacles. The white is free space. Okay, so you want to stay inside the free space. So you create a function L of x. Here I called it v of x0, or v of 0x. So v at time 0 as a function of x, which represents your initial data of what's safe and what's unsafe. And then, based on the dynamics, you can compute, that's an unsafe trajectory. That second one is a safe trajectory. So you can do this Hamilton-Jacobi computation, which is computed here. So there's the red set, which represents the interior of the red set represents the controlled invariant set for all time based on that Hamilton-Jacobi computation. Okay, so here it is in a top-down view, and the model that we're using is just this 4-dimensional model of the turtlebot. And you can see, so it's a 4-dimensional model, and it's projected down into the XY position. So this is safe because this is a slice based on an orientation which is pointing in that direction, right? So that point here on the boundary is safe, but these points here are not safe because at that orientation, because it would push you right into the obstacle. Okay, so that can give us a filter. So this is the safe set boundary now, and it gives us not only a filter, but a control law to use when we hit the boundary. So now the theory is basically the same as before. And what we've been working on is really how to compute this reachable set and update this reachable set as you're getting images in real time. So how do you do local updates to this reachable set as you're getting the perceived information through the sensors? And so we've worked on a variety of sensors, both some maybe a radial sensor or a kind of that field of view sensor that I've shown there. And our perspective has been to assume that everything we can't see, so everything that's outside of the sensed regions, we'll assume that's an obstacle, and then we'll carve away that obstacle as we move the vehicle through the environment and get more and more information. Okay, so that's basically the idea of the algorithm. This is just animating that. So as it's moving, it's getting a bigger field of view. So you're able to update it's your initial function L of x that you update as you get new images, and then you recompute. And to recompute, we're using a localized version. We're just updating, we're capturing the previous computation, and we're just updating on the boundary as the field of view changes. Okay, so we've got a couple of papers that just came out this past year on how we update using warm starting, so using the previous Hamilton-Jacobi computation from the previous image to warm start the next one. And then how we use locality and X to get fast updates. This is assuming that the environment isn't changing. It's a static environment. So once we've labeled something in the environment as safe, it's going to remain safe. Okay, so basically this Hamilton-Jacobi filter comes in right before the control law is applied to the robot. So we do everything, but we've also got this safety verifier based on this separate SLAM channel that we're using as a safety verifier. Okay, I think in the interest of time, I won't show that video, but I will conclude with just this, a little bit of a summary. So the tutorial has been based on a dynamics and control perspective of level set methods and using them for reachable set computation. And then in this last part of the tutorial, I've focused more on really current work that we've been doing in incorporating machine learning, in particular in unstructured environments, into this framework. So, so we talked about safety from reachability analysis and also simplicity from a hybrid system representation. We talked about one paradigm in ability to learn from new information, which was this safe learning paradigm, which assumed, I would say, even though they were like big fans, they were fairly gentle disturbances. So the questions there are, how do we update based on what we're learning? How do we update the reachable set? And then we kind of pushed it in a direction where we're interested in perception problems and really using these reachability-based methods in real time in navigation problems where we're using learning and perception. So we talked about supervising learning using optimal control as well as local updates to reachable sets. And I didn't talk about this, but there's another thread of work going on in my group in computing risk-sensitive reachability for problems, so risk-averse control schemes. All right, so with that, I'd like to conclude and really just thank many of the same students I thanked before, but the people that worked on the safe learning were Jaime and Kene. Kene has gone to Uber. Jaime is now a professor. He's just starting at Princeton. And many of my current students, including, I've got a whole bunch graduating this year. So let's see, Samuel's graduating, Margaret, David, and Sylvia, and Vicens are all graduating this year, all out on the faculty job market, which is a little crazy right now. And I'd like to thank the funding agencies for this work. Thank you very much.